So what if I told you that the perfect blueprint for a $5 trillion, 300 mile per hour American super train comes from a brainless, single-celled puddle of slime?
I mean, it sounds like science fiction,
Yeah.
right? Or like a late night punchline.
Yeah, exactly.
But when you actually look at the raw mathematics of network survival, that mindless organism holds the key to, well, the most ambitious infrastructure project in human history.
Welcome to another deep dive. Today we have a really specific mission. We are unpacking this truly massive, radically different concept of operations essay.
Right, and it's paired with a national architecture paper.
Yeah, and this material, it proposes a complete reinvention of how we think about a United States Maglev, that's Magnetic Levitation Infrastructure Network. And I just want to set expectations right up front for you listening. This isn't some hand-wavy, wouldn't it be cool to have flying trains kind of pitch.
Oh, far from it. The sources we're digging into today are incredibly rigorous. We're analyzing actual Federal Railroad Administration reports, operational logistics from Union Pacific.
Peer-reviewed biological research, too.
Well, exactly. And hard international rail benchmarks, specifically looking at Japan's ongoing maglev construction.
So the ultimate goal of our deep dive today is to basically deconstruct a myth. I mean, we all have this romantic idea of a coast-to-coast super train.
The golden spike all over again.
Right. You take a map, you take a ruler, and you just draw this bold, perfectly straight line from New York to Los Angeles. But this paper argues that drawing a line across the country is actually a catastrophic starting point.
Yeah, it's a terrible idea from an engineering standpoint.
So we're going to explore how looking at biology, the unforgiving, brutal geometry of physics, and the American heartland provides a mathematically and structurally superior roadmap.
And really, the overarching theme here is stripping away political vanity. We've kind of been taught to think about national infrastructure as a series of grand symbolic gestures, right?
Yeah, connecting our most famous coastal cities.
Exactly. But this deep dive asks a completely different question. What does a functional, living, breathing, trillion-dollar infrastructure build actually require to just, survive its own creation?
Let's jump straight into that bizarre hook then, a slime mold.
Yeah, the slime mold.
The source material leans really heavily on this specific 2010 paper. It was published in the journal Science, and it's about an organism called Physarum polycephalum.
Basically a yellow slime mold.
Right. And the essay uses the behavior of this slime mold to define a concept called network topology. So break that down for us. What exactly is topology in this context?
Well, topology at its core is the mathematical study of properties that are preserved through the deformation, twisting, and stretching of objects.
Okay, that sounds really abstract.
It is, but when we apply that to networks like transportation or communications, topology is just about the arrangement of nodes and links. How do things connect to each other?
I see.
So the researchers in that 2010 science paper did something brilliant. They took this brainless slime mold, placed it on an agar plate, and surrounded it with oat flakes.
And the oat flakes weren't just scattered randomly, right? There was a point to it.
Right. They were placed in a very specific pattern that perfectly mirrored the geographic locations of major cities surrounding Tokyo.
Oh, wow.
Yeah. The slime mold itself started at the center, representing Tokyo, and over the course of about 26 hours, the organism grew outward to reach the food.
But it didn't just grow in a giant solid blob, did it?
No, it formed a highly complex network of interconnected tubes to transport nutrients back and forth.
And here's the crazy part. When the researchers compared the network the slime mold built to the actual highly efficient Tokyo rail system, which was designed by generations of human engineers.
They were practically identical.
Which is just mind-blowing to me.
It really is. The organism, driven purely by this biological imperative to survive and transport nutrients efficiently, somehow solved a highly complex spatial engineering problem.
But the crucial takeaway from the source material isn't just that the slime mold drew a good map, right? It's how it drew the map.
Exactly. The organism doesn't build a massive, intricate spider web where every single oat flake connects directly to every other oat flake.
Because a spider web is too expensive. I mean, if you are a slime mold, every millimeter of tube you build costs cellular energy.
Right. If you build too many connections, you exhaust your resources and die.
Which is exactly the same way a country exhausts its capital if it tries to build a high-speed rail line connecting every single mid-sized town to every other mid-sized town.
Exactly. The slime mold strikes this exquisite balance between three things: the cost of building the network, the efficiency of transporting the nutrients, and fault tolerance.
Fault tolerance meaning like resilience.
Yes. If a researcher comes along and cuts one of the slime mold's tubes with a scalpel, the organism doesn't starve.
It just reroutes.
It survives because it builds strong, vital trunks to carry the bulk of the traffic, and then it creates a minimal, highly calculated number of resilient loops.
Just enough detour paths.
Right, so that if a primary trunk is severed, the flow of nutrients can reroute without the whole system collapsing.
I want to try an analogy here to just kind of ground this for anyone listening. Let's think of the slime mold's map as an architect's preliminary blueprint.
Okay, I like that.
So the slime mold is the architect saying, okay, to make this building functional and survive an earthquake, we need a load-bearing pillar here, a central corridor here, and an emergency stairwell here. It dictates the overall spatial relationship, right?
That captures the essence of topology perfectly. The blueprint gives you the structural necessity. It tells you which cities absolutely must be connected to form the essential skeleton of the country.
But, and this is a massive pivot in the essay, a blueprint isn't the physical building. Just knowing where the corridors should go doesn't mean you can instantly manifest them in the real world.
No, definitely not.
Because once you step off the architect's drafting table and onto the construction site, you run into what the source describes as brutal and non-negotiable geometry.
And this distinction right here separates the dreamers from the builders. The biology tells you which cities need to be linked. But the physical geometry of magnetic levitation acts like these inflexible draconian zoning laws.
It forces the architect to design a rigid, unyielding structure.
Right. You have to constantly remind yourself what maglev actually is. According to the Federal Railroad Administration and the SCM-AO of V project data cited in the text, maglev absolutely requires a dedicated, grade-separated guideway.
So if you're listening and you're picturing an Amtrak train that just, goes a bit faster.
Erase that image completely.
Yeah, throw it out.
We are talking about a vehicle that hovers inches above a concrete track, propelled by powerful electromagnets operating at roughly 300 miles per hour.
It cannot run on standard steel wheel train track.
Oh, it cannot share a right-of-way with a slow-moving freight train hauling coal. You are imposing an entirely new physical paradigm onto the landscape, and the curvature required for that guideway is entirely unforgiving.
The essay points to the Japanese benchmark for this, right? The Yamanashi test line.
Yes. The minimum curve radius they use is 8,000 meters, with grades or inclines up to 4%.
Let's visualize that 8,000-meter radius for a second. That is roughly 5 miles. Meaning, if you were laying track and you want to make a turn, the circle you would draw to create that curve has a radius of 5 miles.
To give that some comparative scale, the text notes that the California High-Speed Rail Project, which is a traditional steel wheel on steel rail system designed for about 220 miles per hour, uses design examples with a 22,000-foot radius.
Okay, so how many meters is that?
That's roughly 6,700 meters. So maglev, because of its extreme 300-mile-per-hour top speed, demands sweeping arcs that dwarf even traditional high-speed rail requirements.
Wait, hold on a second. I'm looking at this and thinking about modern roller coasters or even fighter jets. The train is levitating, right?
Right, it's hovering.
It doesn't have wheels grinding against steel rails that might cause a derailment. So if it's hovering, why can't it just bank steeply and carve a tight turn? Why can't it just tilt into the curve like an airplane does?
Well, the limitation isn't the train's ability to stay on the track. The magnets could theoretically hold the train in a much tighter curve. The limitation is the human body sitting inside the cabin.
Oh, the G-forces.
Exactly. At 300 miles per hour, you are effectively flying an aircraft mere feet off the ground. The G-forces generated by entering a tight curve at that speed, even with a perfect banking angle, would be violently intolerable.
I mean, passengers would be crushed laterally into their seats.
Spilling drinks, getting extreme motion sickness, or potentially even blacking out.
So an airplane gets away with it because it has the entire three-dimensional volume of the sky to carve massive, imperceptible arcs over hundreds of miles.
Exactly. While a train is tethered to the two-dimensional surface of the Earth, it has to navigate around real physical obstacles like mountains, property lines, cities.
But because of those G-forces, the fundamental rule of maglev geometry emerges. It demands straight lines.
Straight lines. You cannot take a maglev route and snake it through existing, winding 19th century freight corridors that dodge around every river bend and small town. It requires absolute, disciplined straightness.
Which means our architect's blueprint from the slime mold has to be drawn with a steel ruler.
That's a great way to put it.
And this absolute requirement for straightness completely shatters the traditional wisdom of where we should build this network first. If we can't weave through dense historic infrastructure, we have to find places where we can lay down massive, straight, concrete guideways.
Which leads the essay to a really crucial question. What is the optimal length for one of these straight lines?
Right. And this brings us to the concept of the 150 to 500 mile rule. And I feel like this is the exact moment the romantic notion of the transcontinental supertrain dies.
It really is. The foundational principle of a rational, economically viable maglev network is not to connect everything at once.
The essay states very clearly, do not attempt to build a literal coast-to-coast line as your opening move.
Right. The Federal Railroad Administration uses a very specific cost-benefit framing for high-speed rail. Maglev has a distinct, fiercely competitive transportation niche.
And where is that niche?
It belongs in extremely high-density corridors connecting major city pairs that are roughly 150 to 500 miles apart.
Let's break down the why of those specific numbers for everyone listening.
Yeah.
Why does the magic fade under 150 miles? Think about your typical travel experience. If you were going from, say, Philadelphia to New York or Milwaukee to Chicago, how much of your travel time is actually spent moving at top speed?
Very little of it. Most of the friction in short-distance travel is what the FRA calls station access and egress.
Right. You have to leave your house, you drive or take a local subway to the main terminal, you park, you navigate the station concourse, you wait for boarding.
And then you take the 45-minute high-speed trip.
Yeah, and then you arrive, navigate the destination station, hail a cab, and sit in city traffic to get to your actual hotel or meeting.
The access and egress time completely consumes the trip.
So if you build a multi-billion-dollar maglev line for distance under 150 miles, the 300-mile-per-hour top speed simply doesn't have enough runway to make up for the inherent hassle of getting to and from the stations.
It's exactly. The passenger looks at their watch and realizes that driving their own car from driveway to driveway or taking a conventional 100-mile-per-hour regional train takes roughly the same amount of total time.
And often for far less money and hassle. Okay, so under 150 miles, the immense capital cost of maglev doesn't yield a meaningful time advantage over existing options. That explains the floor.
Right.
What about the ceiling? Why cap it at 500 miles? I mean, why wouldn't a traveler want to take a maglev from New York to Los Angeles instead of flying?
Commercial air travel reasserts its dominance once you cross the 500-mile threshold, and it does so purely through the brutal math of cruise speed.
Because planes are just faster.
Much faster. A standard commercial jetliner cruises at around 550 to 600 miles per hour. Maglev tops out at roughly 300.
So the plane is literally moving twice as fast.
Over a short distance, a plane's speed advantage is negated by the theater of airport security, taxiing, and holding patterns.
But over a 1,000-mile or 2,000-mile journey.
The jet's sheer velocity crushes the maglev. The traveler will gladly endure the TSA line in the cramped middle seat because a cross-country flight takes 5 hours, whereas a cross-country maglev, even moving at 300 miles per hour and assuming no major stops, would take 10 or more hours.
That reframing is essential. If I'm traveling 200 miles, I want the train because I get to bypass the airport entirely. If I'm traveling 2,000 miles, the airport headache is suddenly worth it because the plane cuts my travel time in half.
The conclusion is inescapable. A national maglev network cannot be one giant symbolic ribbon. It has to be assembled as an overlapping chain of highly profitable, high-utility segments that each exist within that 150 to 500-mile sweet spot.
You can eventually cross the continent, but the continental system must emerge as a lattice of these functional regional blocks. So if we accept that 150 to 500-mile straight lines are the fundamental building blocks of this technology, we have to find a place flat enough and unconstrained enough to lay the first one down.
And this is where the source material drops a massive geographic revelation.
Yeah, the smartest place in America to build the first segment of a multi-trillion-dollar transportation network isn't New York.
Nope.
It isn't the California coast. It isn't even the eastern seaboard. It is Nebraska.
Nebraska. And the author makes a really compelling case that this is not some contrarian gimmick. It is the most rational inland starting point in the country.
But only if you fundamentally understand the architecture of what a massive technological system requires to keep itself alive, right?
Right.
So the essay details an architecture it calls the Nebraska Dual Center Engine. Let's dive deep into this because it challenges everything we assume about transit hubs. The network in Nebraska requires two entirely distinct hearts.
Okay, so the first heart is the passenger gateway. The source identifies the Omaha and Lincoln area for this role. Based on 2024 Census Quick Facts estimates, Omaha has a population of around 489,000, and Lincoln sits near 300,000.
So combined, you have nearly 800,000 people.
That provides a viable population base to generate initial ridership. Omaha and Lincoln serve as the front door to the system.
They provide the intermodal transfers to airports and highways. They offer the institutional and corporate presence.
And crucially, they provide the political legitimacy. When politicians cut the ribbon on the network, they do it at a beautiful glass-walled station in Omaha.
Right, the photo op. But then there is the second heart, the industrial heart. And this is located about 4 hours west in a town called North Platte.
Now, North Platte has a population of just over 22,500 people. It is a small town on the plains, but it is home to something of staggering infrastructural importance.
Union Pacific's Bailey Yard.
Yes. Calling Bailey Yard a train yard feels entirely inadequate. According to Union Pacific's own operational data, it is the largest railroad classification yard in the world.
How big is it exactly?
It spans roughly 2,850 acres. It processes upward of 10,000 rail cars every single day.
Wow.
Geographically, it sits right at the crucial intersection of major east-west and north-south freight corridors.
Now let me push back on this, because if you're listening to this, you might be highly skeptical. Are we really saying that a town of 22,000 people is going to be the central nervous system of a high-tech network that will cost trillions of dollars?
It sounds counterintuitive.
Why on earth wouldn't a project of this magnitude just build its massive maintenance facilities right outside of a gigantic hub like Chicago or Dallas?
The answer lies in the sheer, unyielding physical footprint required to maintain a levitating train network. We suffer from a conceptual bias where we view transportation purely as a ridership device. We only think about the vehicle moving people from A to B.
But the essay vehemently stresses that Maglev must be understood as a system of systems.
A system of systems.
So walk us through the actual mechanics of that. What does that require on the ground?
The glossy passenger trains are just the tip of the iceberg. To run a national Maglev network, you need vast expanses of land for heavy maintenance facilities where you can lift and repair 300-mile-per-hour vehicles.
You need colossal industrial factories for precision guideway fabrication.
Right, because earlier we established you can't just order a Maglev track on Amazon or buy it from a steel mill.
Exactly. The tolerances for a guideway hosting a vehicle moving at 300 miles per hour are microscopic.
The concrete often has to be cast and cured on-site or at massive climate-controlled regional depots to account for thermal expansion and millimeter-perfect alignment.
That sounds incredibly space-intensive.
It is. You also need space for turnout-free trunk dispatching. You need huge substations for traction power management and electrical grid interfacing. You require operations control centers, emergency staging areas for specialized rescue equipment, and sprawling yards for overnight fleet redistribution. And North Platte already possesses this specific industrial DNA. It is culturally, geographically, and operationally hardwired for massive rail scale. Attempting to find 3,000 acres of affordable, industrially zoned, environmentally cleared, rail-accessible land on the outskirts of Chicago is, well, it's a fool's errand.
That land is heavily constrained.
Prohibitively expensive and surrounded by suburbs that would litigate a heavy industrial project into oblivion. North Platte offers the vast, unconstrained space necessary to build the literal machine room of the national network.
I am fascinated by that concept of the machine room. This dual-center architecture essentially hides the technical metabolism of the system from the consumer.
That's the beauty of it.
The people buying tickets, imagine the network begins and ends in the pristine stations of Omaha and Lincoln. But the grinding industrial heart that actually keeps the levitating trains running, the power flowing, and the guideways repaired is humming away out in North Platte.
It's a brilliant, pragmatic separation of the glamorous map from the unglamorous operating reality. It represents a much healthier, more realistic design philosophy than pretending every new national system needs its gritty maintenance yards situated in a crowded, hyper-expensive coastal corridor.
You build a machine room where there is room for the machine.
Exactly.
Okay, so we have our machine room established in North Platte and our glossy passenger doors open in Omaha and Lincoln. We are firmly planted in the Nebraska core. Now, we bring the logic of our slime mold back into the picture.
Right, time to grow the network.
We're going to apply that biological imperative to grow the first vital trunks of the system outward from this Nebraska hub. The essay outlines this as Phase IA. the inland skeleton.
And the design of this skeleton adheres strictly to the slime mold's topology. It seeks the smallest number of powerful trunks carrying the highest value of traffic, integrated with only the most essential loops to guarantee resilience.
Let's trace this prairie skeleton on the map. The first great tendon extending from the core is the eastern trunk, Omaha to Chicago.
This is approximately 500 miles, so it's hitting the absolute perfect upper limit of our sweet spot.
And this isn't an arbitrary line drawn on a blank map, is it? The source anchors this route in actual Federal Railroad Administration planning history.
Yeah, the FRA's long-standing Chicago to Council Bluffs-Omaha Regional Passenger Rail Study explicitly establishes the viability of this corridor. Tying into Chicago Union Station is structurally critical.
Because Chicago is the hub.
Exactly. A Nebraska-first system that fails to capture Chicago early in its life cycle remains strategically incomplete. Chicago serves as the indispensable eastern hinge of the interior United States.
It is the exact geographic and economic choke point where a regional Midwestern line evolves into a viable candidate for a national network.
Chicago is the gateway.
So that's our massive eastern push. Moving the opposite direction, we have the western trunk, Lincoln and North Platte extending out to Denver.
The text points out that this route capitalizes on long, straight reaches and moderate grades across the High Plains. It bridges the Great Plains directly to the foot of the Rocky Mountains.
And from a network logic perspective, why Denver?
The Denver connection is how the Nebraska Corps secures a true western face long before attempting the incredibly arduous terrain and hostile politics of the Pacific Coast.
That makes sense.
Furthermore, it plugs the Maglev network directly into the existing Federal Corridor ID framework, which is currently studying traditional rail expansion along the Colorado Front Range. It utilizes the natural geography of flat plains to build operational momentum and public trust.
Now here is where the network architecture gets deeply interesting and where the slime mold concept of the resilient loop comes into play.
The southern hinge.
Yes, the essay proposes a southern hinge. This line drops south from Omaha down to Kansas City and then cuts east from Kansas City over to St. Louis.
Now, if engineers were purely trying to connect cities in the cheapest way possible, they might just draw a hub-and-spoke star formation with Omaha at the dead center.
But the author explicitly warns against a brittle star architecture, right?
Definitely. A rigid star formation where every single peripheral city rates directly through one single central hub is highly vulnerable to cascading failure.
What happens if it fails?
If there is a catastrophic power grid failure in Omaha, a severe winter storm, or a structural issue at that central node, the entire Midwestern network is instantly paralyzed. That is the exact fragility the slime mold evolves to avoid.
Let's use a plumbing analogy to visualize this.
Yeah.
Think of this Kansas City to St. Louis route like a detour valve in your home's water system.
Oh, that's a good way to look at it.
Right. If the main pipe, our direct Omaha to Chicago trunk, gets clogged or bursts, the whole interior network doesn't suddenly run dry. The trains and the passenger traffic can simply flow down to Kansas City, across the lower pipe to St. Louis, and then angle back up to Chicago.
The slime mold demands resilience, and that southern loop delivers it. It ensures the interior network has a secondary path to Chicago, a future-proofed path toward the southern states, and an alternate vector toward the East Coast.
And again, this aligns perfectly with existing passenger rail planning gravity around the Missouri and Illinois DOTs. Kansas City ceases to be just a terminus. It becomes the structural hinge that actively prevents a single point of failure collapse.
Finally, to round out the skeleton, we have the northern wedge, Chicago up to the twin cities of Minneapolis and St. Paul.
The author makes a very specific point here, though. You do not attempt to force an awkward diagonal line directly from Nebraska through the wilderness to Minneapolis.
Instead, you route it out of Chicago, harmonizing with federal planning that already deeply understands the economic gravity of the Chicago-Milwaukee Twin Cities corridor.
The overarching lesson of this phase isn't that Maglev must slavishly copy every single underperforming Amtrak route. The lesson is that decades of U.S. rail planning already reveal where the undeniable gravitational pull of human demand lies.
This inland skeleton, Omaha to Chicago, Omaha to Denver, the resilient loop through Kansas City and St. Louis, and the branch to the Twin Cities, forms a legible, highly functional interior grid.
It abandons the vanity of coastal connections for the rugged utility of the plains.
So we've established where the lines must go to form this skeleton, but drawing lines on a topographical map is the easy part.
Yeah, drawing lines is free.
The essay shifts gears entirely here to outline a ruthless doctrine for how these guideways must be built to survive the reality of American infrastructure development.
Which brings us to the build doctrine. And the core philosophy of this doctrine is straightness over sentimentality.
This section of the essay will undoubtedly trigger the most intense political friction.
Oh, absolutely.
The author insists that Maglev guideways must absolutely not be dragged through every single downtown center simply to placate local mayors, chambers of commerce, or historical societies.
And equally important, they should not blindly follow legacy, winding freight tracks, simply because a right-of-way happens to exist on paper.
Because, as we established with the brutal geometry, a 300-mile-per-hour levitating train cannot negotiate the tight curves of a 19th century river route.
So what does the doctrine mandate instead?
It mandates that guideways must follow modern, straight transport corridors, interstate highway medians, massive utility line easements, and they should rely heavily on peripheral through stations or short, lower-speed connector spurs to grant passengers access to cities.
Wait, I have to push back hard on this. Put yourself in the shoes of a local taxpayer.
Okay, I'm listening.
You are telling me my state is going to contribute billions of dollars toward a futuristic super train, and instead of pulling grandly into a beautifully restored downtown terminal, it's going to drop me off at a concrete edge station out near the highway bypass past the suburbs.
I know, it sounds awful.
That sounds like a devastatingly poor rider experience.
The initial shock is completely understandable, but the author demands we look at the merciless physics and economics of downtown penetrations. Routing a maglev into a dense downtown requires deep-bore tunneling under skyscrapers.
It's just incredibly complex.
You're navigating a labyrinth of existing subway lines and sewer mains, and utilizing sharp speed-killing curves. To accept this doctrine, the public must adopt a completely new mental model. You cannot think of maglev as a train.
The correct mental model is aviation corridors pinned to the ground.
Aviation pinned to the ground, that phrase completely changes the framing.
Consider commercial aviation. You would never demand that a Boeing 747 land in the center of the city square just because it's slightly more convenient for the passenger stepping off the plane.
The noise, the physical footprint, the danger, and the sheer impossibility of the maneuver dictate that we place the airport on the periphery of the city.
Right. The traveling public accepts that they must commute 30 minutes to the edge of town to board the massive high-speed vehicle. Maglev requires that exact same spatial respect for its velocity, its mass, and its massive turning radius.
So to manage this, the essay proposes a strict hierarchical station architecture. You only build a true metropolitan terminal deep within a downtown core if the projected ridership and the massive real estate transit-oriented development returns absolutely, mathematically, justify the astronomical cost of the deep tunneling.
Otherwise, you build through running edge stations.
Exactly. These stations preserve the pristine straightness of the trunk line, allowing the train to maintain its speed without forcing a massive, multi-billion-dollar detour.
And then at the base of the hierarchy, you have the logistics nodes like North Platte, which aren't designed to be passenger monuments at all.
It's infrastructural triage. Downtown access must be fiercely earned, where it fundamentally alters the economics of the route, rather than treated as a religious obligation at every single municipal stop.
This uncompromising approach extends to the physical guideway itself, right? The doctrine insists that the main trunk lines must be built as dual guideways, meaning 2 tracks side by side from day one.
So no single track compromises to save a few bucks up front.
None whatsoever.
The author cites older FRA cost reports that explicitly warn against single-track concepts, labeling them as dangerous false savings. Yes, laying down one track cuts the initial capital costs significantly.
But there's a trap there.
A massive one. The very moment the network achieves success, the moment you need high-frequency bidirectional traffic to meet demand, a single track transforms into a fatal capacity trap.
Because you can't have 2 trains going opposite directions on one track. You'd have to build sidings where one train pulls over to let the other pass.
But if the trains are moving at 300 miles per hour, pulling over completely ruins the schedule, destroys the speed advantage, and permanently caps the revenue the line can generate.
Exactly. In open country America, where land acquisition is relatively cheap compared to urban centers, the capital must be poured into absolute straightness, total grade separation, extreme wind and weather hardening, and building a full dual-track trunk.
You overbuild the capacity of the skeleton so the network can breathe and expand for a century.
This stark warning about the sheer expense of tunneling into downtowns really sets the stage for the most sobering, frankly, terrifying part of this entire deep dive. Because we can't talk about infrastructure without talking about the price tag.
We are moving into the trillion-dollar arithmetic.
And if you're listening to this on your commute or at home, brace yourself. The numbers we are about to unpack are staggering.
The author goes to great lengths to ground these financial models in a blend of historical context and harsh contemporary data, ensuring this isn't just back-of-the-napkin guesswork.
Historically, if we look back at FRA estimates presented in 2004 dollars, Maglev construction was estimated to cost anywhere from $40 million to $100 million per mile.
And that variance was entirely dependent on terrain. A relatively flat rural mile might cost $27.4 million, while a dense, complex urban mile was pegged at roughly $98.5 million.
But the essay urgently points out that those 2004 numbers belong to a bygone era. We now have a much more recent, much more alarming benchmark that the author calls the urban warning shot.
And that is the proposed Baltimore-Washington SEM-Maglev project.
The SEM-Maglev project aims to connect Baltimore, Maryland, and Washington, D.C., covering a distance of roughly 33 to 35 miles.
Because it is attempting to navigate the Northeast Corridor, one of the most densely populated, heavily built up and historically complex landscapes in North America, the project requires anywhere from 70 to 83% of the entire route to be built in deep subterranean tunnels.
And what was the estimated capital cost to construct those 35 miles?
Nearly $20 billion.
I want everyone to let that specific math sink in. $20 billion for approximately 35 miles of track.
That approaches $570 million for a single mile.
That is just incomprehensible.
To validate that domestic warning shot, the author also pulls an international benchmark. Japan's JR Central is currently constructing the Chuo Shinkansen, a genuine superconducting maglev line.
The specific section running from Shinagawa in Tokyo to Nagoya was forecast in October 2025 at an incredible 11.0 trillion yen.
When the author applies the Federal Reserve's March 2026 conversion rate, that single Japanese segment equates to approximately 68.9 billion US dollars.
So using these sobering modern benchmarks, the author models out the financial reality of the Nebraska-centered inland skeleton we just discussed, Phase IA.
This phase comprises roughly 2,210 route miles of predominantly open country guideway, modeling the cost at $260 million per mile, and then adding a 15% allowance for what is called the systems layer,
which accounts for the massive stations, the maintenance depots, the traction power substations, and the control software.
Exactly. So Phase IA totals about $660.8 billion.
Keep in mind, that is just the preliminary skeleton. The essay then models out Phase IB.
This phase introduces a Texas lower arc, a massive expansion running from Kansas City south to Dallas-Fort Worth, over to Houston, and down to San Antonio.
Adding Texas brings the total network to roughly 3,150 route miles. Depending on the low or high per mile cost assumptions used, that Phase IB build lands anywhere from approximately $941 billion to $1.268 trillion.
We have officially crossed the trillion-dollar threshold.
And the essay doesn't stop there. It projects the ultimate cost of a fully realized national backbone, a sprawling network encompassing 9,500 to 11,000 route miles across the country.
The estimated price tag for that final vision, anywhere from $2.85 trillion up to $4.95 trillion.
Which retroactively validates the author's earlier assertion that a legitimate U.S. Maglev program is not a few $100 billion project that could be tucked into a standard highway bill.
No, it is a multi-trillion-dollar epical undertaking.
My visceral reaction to reading those numbers, I am reeling. $5 trillion. For context, $5 trillion is larger than the gross domestic product of many advanced industrialized nations.
It's on another level completely.
We are talking about a mobilization of capital that rivals the entire interstate highway system, or the Apollo space program, adjusted for modern inflation. It is an almost incomprehensible sum of money.
It is breathtaking. But when you step back and connect these numbers to the overarching theme of the essay, the sheer shock of the math proves the central thesis.
Inland, open country maglev, where you are building elevated guideways across flat, relatively unpopulated agricultural land, and tunnel-heavy, metropolitan coastal maglev are entirely different economic species.
You cannot even discuss them in the same financial breath.
The cost difference between a $260 million open country mile and a $570 million deep tunnel urban mile is an unbridgeable chasm.
Precisely. You simply cannot launch a $5 trillion national infrastructure project on blind hope and glossy renderings. You cannot begin by attempting to bore $20 billion tunnels under the historic foundations of Baltimore and legitimately expect the American public to grant you the endless funding required to finish it.
You must systematically prove that the technology works, that it is undeniably fast, and that it can generate robust operating revenue in the cheaper, lower-friction, open-country corridors first.
The inland Midwestern lattice is not a detour from the grand national vision. Mathematically, it is the only financially credible road into it.
This catastrophic cost discrepancy provides the perfect, unavoidable explanation for why the final, most famous pieces of the map, the east and west coasts, must be fiercely protected and left for last. Which brings us to our final major area of exploration, earning the coasts, and what the author brilliantly terms the social permission structure.
The east and west coasts possess what the paper describes as massive corridor gravity. Everyone intuitively knows the overwhelming passenger demand is there.
You have the legendary Northeast Corridor, you have the Southeast High-Speed Rail concept envisioned from Washington, D.C. down through Atlanta. You have the Cascadia Corridor connecting Vancouver, Seattle, and Portland in the Pacific Northwest.
And of course, California. The source points out that the California High-Speed Rail Phase 1 project is the ultimate case study.
The raw demand along the San Diego to Los Angeles up through the Bay Area to Sacramento axis is undeniable.
The demand is undeniable, but the source explicitly characterizes these coastal regions as vicious in delivery.
Vicious in delivery. That paints a grim picture of infrastructure development.
Consider the paralyzing constraints. You have some of the most dense urbanization on the planet. You have unforgiving geology, with mountain ranges pushing right up against the sea and active seismic fault lines.
You have incredibly congested shared freight corridors that cannot be disrupted.
You face intense, highly organized environmental sensitivity. And you encounter punishing terminal complexity when trying to route a new guideway into the heart of Los Angeles or San Francisco.
Building high-speed infrastructure in these zones is not an engineering project. It is a grueling, decades-long trench war of litigation and property acquisition.
And the essay provides a very real, very recent example of what happens when a Maglev project gets bogged down in those exact coastal battles.
The source notes that in August 2025, the United States Department of Transportation announced that the FRA was canceling over $26 million in previously awarded grants for the Baltimore-Washington SCMA-Maglev project.
The federal officials executing the cancellation cited a litany of cascading failures. Chronic project delays, ballooning cost overruns, intense and highly organized local opposition from communities along the route, and deeply unresolved environmental impacts.
And I want to make a crucial impartial note here, exactly as the essay does. Regardless of where any listener stands politically on the opposition to the SCMG-LAE project, whether you fiercely support the local environmental and community groups or you back the tech developers, the fundamental delivery lesson remains completely unavoidable.
The lesson being, if your nation's very first introduction to Maglev technology is an attempt to shove it into the hardest, most expensive, most politically fraught urban corridor in America, and that project inevitably gets mired in endless lawsuits, protests, and budget explosions.
The public learns a very specific, deeply negative lesson.
The public learns to permanently associate the very word Maglev with litigation, eminent domain trauma, endless construction delays, and catastrophic programmatic failure. It poisons the well for the entire technology before a single commercial ticket is ever sold.
So, synthesizing this strategy, the essay argues that you must start in Nebraska. You build the inland, straight trunks across the plains where land is relatively open, politics are less dense, and construction is vastly faster.
The trains begin running at 300 miles per hour, safely, reliably, and visibly. The American public sees the technology actually working. It generates real-world revenue.
And by successfully executing that inland skeleton, the technology slowly earns a social permission structure from the voters to eventually tackle the brutal multi-billion-dollar coastal penetrations decades later. So my question is this massive architectural roadmap basically just an elaborate public relations strategy disguised as an engineering timeline?
While it heavily leverages public perception, calling it a PR strategy is too narrow. The author frames it fundamentally as an economic survivability strategy.
A PR strategy is simply about making taxpayers like you An economic survivability strategy is about generating enough actual physical momentum, operational data, and operating capital to prevent the project from being canceled by the next congressional administration.
The inland engine, the Omaha to Chicago to Denver to Texas lines, must become physically and economically robust enough to literally subsidize the grueling coastal tunneling.
The easy miles have to pay for the impossibly hard miles.
Precisely. By the time the network finally reaches the coasts, those coastal connections change from being an impossible multi-trillion-dollar pipe dream on a political poster into the highly plausible final chapters of an infrastructure system that is already living, breathing, and functioning across the entire interior of the country.
Okay, let's take a deep breath and synthesize this incredible journey we've just been on. We started this deep dive looking closely at the biological logic of a brainless slime mold, learning that an optimal survivable network requires strong, vital trunks and calculated resilient loops, not a sprawling, fragile spiderweb.
We learned that the merciless physics of 300-mile-per-hour magnetic levitation absolutely demands straight lines. You cannot subject human bodies to fighter jet G-forces by bending a train like an airplane.
We discovered the strict parameters of the 150 to 500-mile rule, realizing that Maglev's true power lies perfectly sandwiched right between the driveway convenience of a personal car and the 600-mile-per-hour cruise speed of a commercial jet.
We utilized a 22,000-person town in Nebraska North Platte, home to the sprawling Bailey Yard, as the massive 3,000-acre industrial machine room for the entire national network.
Deliberately keeping the glossy passenger stations separate from the unglamorous, heavy industrial reality of guideway fabrication and fleet maintenance. We traced a multi-trillion-dollar Midwestern skeleton extending out to Chicago, Denver, and deep into Texas.
And finally, we realized that saving the massive corridor gravity of the East and West coasts for last is the only conceivable way to politically and economically survive the sheer, staggering cost of building this technology.
The essay represents a profound, paradigm-shifting rethinking of how America builds infrastructure. It replaces outdated nostalgia and political sentimentality with the cold, hard truths of geometry, biology, and relentless economic discipline.
It really does.
And before we wrap up today's session, I want to leave you with a final provocative thought to mull over. We spent a significant amount of time debating that build doctrine, the philosophy of treating maglev like aviation pinned to the ground, where trains bypass historic downtowns and instead drop passengers off at massive edge stations out near the highway bypasses.
Yeah, that was a huge point.
If this essay's vision actually comes to pass, how does that physically and culturally reshape American geography? If the most important high-speed transit hubs in the country are suddenly located on the rural fringes of our current metropolitan areas, do those edge stations eventually become the new downtowns?
That's a wild thought.
Do major corporations abandon the old city centers to move their headquarters out to the maglev station? Do entirely new, high-density cities sprout up out of the farmland surrounding the guideway? If a 300-mile-per-hour train makes the space between major cities shrink to a matter of minutes, does the traditional concept of a city limit even mean anything anymore?
It completely redefines everything.
When you look at a map and you realize that a mathematically perfect straight line doesn't just connect two places, it radically alters the economic destiny of everything it touches. That is something for you to ponder the next time you're stuck in gridlocked highway traffic, wishing you could just levitate over it all. Thank you so much for joining us on this deep dive into the sources. We will catch you next time.